Okay, next we get to the math associated with lenses. What we want to come up with here is basically the lens equivalent of something we've seen before, and that was the mirror equation. Okay, recall in the mirror equation, the three distances were related to each other, the object distance, the image distance, and the focal length. We want to come up with the equivalent expression now for lenses. Okay, so let's get to the math. Okay, in order to come up with the mathematical expression that we're looking for here now for lenses, we have to apply the following equation. Recall from last time's folder, refraction at a spherical surface. Okay, that was the following expression, if you recall. This expression here, and there was a sign convention associated with it. Okay, we're going to have to apply that equation here for two surfaces. So for example, right here I have a double convex lens. Light is going to refract from air to glass with this first surface, and then it's going to refract from glass back to air here at the second surface. As I develop the math here behind lenses, I'm going to specifically reference the last problem that I did in last time's folder. That last problem involved the paperweight calculation where I refracted the light across the two surfaces. We're going to apply essentially that situation here. Okay, now what I am about to derive here could actually be derived for any situation involving any lens, but I'm going to derive this for the simplest possible situation, which is simply for a point object that is close to a double convex lens. So I'm going to begin to draw out the following ray diagram. Okay, so right here is a double convex lens like so. Right here is an optical axis. Okay, now the lens itself, like the paperweight example that I did last time, has a thickness associated with it that's referred to as T. And then here is the first surface. There's going to be a radius of curvature associated with it. We'll call R1. Right here is the second surface. There's going to be a radius of curvature associated with it. We'll call it R2. Okay, and then I have right here a point object. We'll just label this as O. That is some distance away here from the first surface. This object distance here is just referred to as DO. And then what we're going to do is we're going to refract light across then the first surface, light that is coming from that object. So I'm just going to draw here two light rays. One light ray coming from the point object just along the optical axis itself, and that then begins to refract through the first surface like so. Okay, and then arbitrarily right here is going to be a second light ray like so, which I'm then going to refract across the first surface. When I do, it's going to refract like so. And the reason for that, by the way, is because we're going from air, where the index of refraction is 1, to glass, where the index of refraction here we're just going to refer to as n, where n is greater than 1. So then therefore I had to kind of bend my light ray down in this direction as I refracted from the air to the glass. And then later on, of course, we're going to refract back into the air again. Okay, now take a look at these two light rays here and here. Notice that they're diverging from each other. So then therefore, if I take these two light rays and extend them back in this direction behind the lens, it looks like those light rays are coming from a point that is back here. Okay, I'm going to label this point right here as O prime. This is the image for the first surface. Okay, now in reference to that paperweight example, we calculated that distance. That distance ended up being negative 18 centimeters. That is the distance from here to here in that example. We're going to refer to this distance here as di prime. Okay, now let's go ahead and apply the equation here across this first surface. So this is the first refraction. So I'm going to have n for air, which is 1 over dO, plus then n for glass over the first image distance here, di prime, we'll call it, equals then n minus 1 over r1, the first radius of curvature. Like so. Okay, now we get to the second refraction. So for the second refraction, what is the object distance? Well, the object distance for the second refraction is this value here. Specifically in that paperweight example, what we did was we took this negative 18 centimeters, we made it positive to be 18 centimeters, and then we added to it the thickness of the paperweight, which was 20 centimeters. That then gave us a new object distance here of positive 38 centimeters. That will then be my new object distance when I apply the equation across the second surface. Okay, before I do, however, before I write the equation itself, let's just go ahead and refract these two light rays here and here across this second surface. When I do, they converge, by the way, like so, to form the final image here. Just referred to as I, and then right here on the diagram is the final image distance now, di. Here's now how we write the second refraction equation. Okay, so now we're going to have n for glass divided by the new object distance. The new object distance, remember, is this distance here. Here's how you write this expression. Like so. Notice how this works in terms of that example from class. This was negative of negative 18 centimeters for just 18 centimeters, plus the 20 centimeter thickness then of the paperweight gave us a total of positive 38 centimeters. Okay, now in the second term, this is going to be n for air over the final image distance here, di, equals then n for air minus the n for glass over the second radius of curvature. That then looks like this. Okay, now at this point, we're going to make what is referred to as a thin lens approximation. I certainly couldn't do what I'm about to do here with the paperweight problem from last time, but I can do so safely here, for example, with this lens. Compare, for example, the thickness of this lens T to the two radii of curvature. Notice that the surfaces of the spheres associated with either side of the lens, well, those spheres are huge. For example, if you look at the sphere associated with this surface on my left, the surface itself is basically tracing out a sphere that is gigantic. It probably fills half the room. The radii of curvature here for this lens are really large numbers compared to the thickness of the lens itself. So then therefore, we consider the thickness T to be negligible for that reason. This is called the thin lens approximation, and it's perfectly acceptable here. Okay, so for the thin lens approximation then, we basically just ignore this term right here, the thickness of the lens itself, and then we end up with these two expressions. Notice that within these two expressions, there is this term here, n over di prime, and this term here, negative n over di prime. Basically what we do now at this point is we just combine the expressions together. When you combine the expressions together, you end up with the following. You end up with this equation here. Like so. Take a look at the right-hand side of the expression. It looks familiar. It's the same thing. Excuse me, the left-hand side of the expression. Take a look at the left-hand side of the expression. It looks familiar. It's basically the same thing as the left-hand side of the expression when talking about the mirror equation. Notice, however, what is missing in all of this. Notice that I haven't said a word about the focus. That is, what is the focal length? And the focal length itself, for example, doesn't even appear on the diagram above. So what is F, the focal length? Well, in order to find the focal length, what we have to do is we have to find the image distance for an object that is placed infinitely far away from the lens. So what I'm going to do is set the object distance in this equation equal to infinity, and then therefore the image distance is equal to the focal length. Watch what happens then therefore as I do. Over here on the left I have 1 over infinity plus 1 over the focal length. Remember, that's the same thing now as the image distance for this situation. And that then equals the right-hand side of the expression. Over here on the left, 1 over infinity is equal to 0. And then therefore you simply end up with this. In other words, the right-hand side of the expression here is 1 over the focal length. Let me go ahead and get rid of this term here to illustrate, like so. So then therefore you just end up with this expression here. Which should look familiar. It's actually the same equation as it was for the mirror equation. This shouldn't be all that surprising. And the reason for that very simply is as follows. Basically what we're describing here, first of all with mirrors and reflection, and now with lenses and refraction, is just geometry. So then therefore geometrically they actually obey the exact same expression. Okay, the difference between the two, however, is as follows. It's basically the right-hand side of the equation. If you recall from mirrors, when you're talking about the focal length is just 1/2 the radius of curvature. However, when you're talking about lenses, 1 over the focal length is the right-hand side of the expression, that is this term right here. The right-hand side of the expression, this term right here, is given its own name. This is referred to as the lens maker's equation. To place the lens maker's equation into context for you, for those of you that wear glasses or contact lenses, and you go to an optometrist, and when you go to the optometrist, you sit in that chair and then they place a device over you, and then they have you look at printed paper or printed words on the wall, and then therefore they adjust the lenses as you read until they can then get your prescription. Okay, what are they adjusting when they're changing from one lens to another? They're changing the radii of curvature. In other words, this equation right here is your prescription. So when you have a prescription written out from the optometrist, the prescription actually is this equation. Okay, specifically in optometry, however, your prescription is referred to as the power of the lens. The power of the lens itself, 1 over the focal length, is this expression here. So depending upon whether or not you are nearsighted or farsighted, how badly you're nearsighted or how badly you are farsighted, that will then adjust the various values here for your prescription. The power of the lens, as it's referred to as, is measured in terms of 1 over distance. It's measured in terms of meters to the -1. This quantity right here, when talking about optometry, is sometimes referred to as a diopter. So that's specifically what your prescription is if you go to an optometrist. As you sit in a chair and they manipulate the lenses, basically what they're doing is they're manipulating the radii of curvature. Okay, now at this point right here, I'm going to go ahead and pause this video. What I want you to do at this point, however, is take a look at my lens maker's equation demonstration in today's folder.